It's 140 million miles away, a journey that takes nearly 9 months. And yet, Mars is the most realistic destination for humanity's next giant leap. But how do we actually get there? What does it take to launch, navigate, and land on the red planet? Today, we break down the science, the strategy, and the staggering complexity of getting to Mars. Why Mars? Mars has captivated human imagination for centuries, and for good reason. It's the most Earth-like planet in our solar system, offering tantalizing possibilities for future exploration and even colonization. As the second closest planet to Earth, Mars presents a unique opportunity for scientific discovery and the potential to answer fundamental questions about the origins of life in our cosmic neighborhood. The red planet's similarities to Earth are striking. It has a day length of about 24 hours and 37 minutes, seasons due to its axial tilt, and evidence of ancient water flows on its surface. These factors make Mars an ideal candidate for studying planetary evolution and the potential for past or present microbial life. But getting there is no small feat: launch windows and timing. One of the most crucial aspects of a Mars mission is timing. Earth and Mars align in their orbits every 26 months, creating optimal launch windows that minimize fuel use and travel time. This alignment is essential for efficient interplanetary travel. Think of it like passing a football to where the receiver will be, not where they are now. Spacecraft must aim for where Mars will be when they arrive, not its current position. These launch windows are relatively short, typically lasting only a few weeks. Miss the window and the mission could face significant delays or become entirely unfeasible. The next favorable alignment won't occur for another 2 years, highlighting the importance of meticulous planning and execution in space exploration, escaping Earth's gravity. But before we can worry about interplanetary trajectories, we need to escape Earth's gravity well. This is where powerful rockets come into play. To break free from Earth's gravitational pull, a spacecraft must reach escape velocity, approximately 11.2 kilometers per second. That's over 40,000 kilometers per hour. The heavier the payload, the more thrust required to achieve this velocity. For Mars missions, NASA has relied on rockets like the Atlas V and SpaceX's Falcon Heavy. These launch vehicles are capable of delivering several tons of payload to Mars' transfer orbit. However, future crewed missions will require even more powerful rockets to transport the necessary life support systems, habitats, and return vehicles, navigating deep space. Once a spacecraft escapes Earth's gravity and begins its journey to Mars, the real challenge of deep space navigation begins. The total trip covers about 300 million miles through the void of space. During this time, the spacecraft must perform several mid-course corrections to stay on target. These trajectory adjustments are crucial because even tiny deviations at the start of the journey can result in missing Mars by thousands of miles. Mission controllers use sophisticated computer models and tracking data to calculate these corrections, ensuring the spacecraft remains on course throughout its months-long voyage. The journey isn't just about staying on course, though. Spacecraft must also contend with the harsh environment of deep space. Solar radiation poses a significant threat to both electronic systems and, in the case of crewed missions, human health. Future Mars missions will need to incorporate robust shielding and possibly artificial magnetic fields to protect astronauts from this constant bombardment of high-energy particles entering Mars' atmosphere. As the spacecraft approaches Mars, it faces perhaps its most challenging phase, entering the Martian atmosphere and landing safely on the surface. Mars' atmosphere is notoriously tricky to navigate. It's thick enough to cause significant heating during entry, but too thin to provide much deceleration for landing. This atmospheric peculiarity has led to the development of complex landing systems. Spacecraft typically use a combination of heat shields, parachutes, and retro rockets to slow their descent. The heat shield protects the vehicle during the initial, high-speed entry phase, while parachutes deploy to further reduce velocity. Finally, retro rockets fire to allow for a controlled touchdown. NASA's recent Mars missions have pushed the boundaries of landing technology. The Perseverance rover, for example, used a sky crane system, a rocket-powered descent stage that lowered the rover to the surface on cables before flying away. This innovative approach allowed for the precise placement of the large, car-sized rover on Mars' challenging terrain. Future human missions. Looking to the future, human missions to Mars will require even more advanced landing systems. SpaceX's ambitious Starship vehicle aims to land on Mars using only its engines, a technique known as propulsive landing. This approach could allow for the delivery of much larger payloads, essential for establishing a sustainable human presence on the Red Planet. The challenges don't end with a successful landing, however. Future crewed missions to Mars will face a host of additional hurdles. Long-term exposure to radiation during the journey and on the Martian surface remains a significant concern. Developing effective shielding and possibly medications to mitigate radiation damage will be crucial for astronaut health. Life support systems must also be incredibly robust and efficient. Recycling air and water, growing food, and managing waste are all critical components of a long-duration Mars mission. These systems need to function flawlessly for years with minimal resupply from Earth. Perhaps the most daunting aspect of a crewed Mars mission is the return journey. Unlike missions to the Moon, where astronauts can return to Earth in a matter of days, a round trip to Mars could take 2.5 to 3 years. This extended duration poses significant psychological challenges for the crew and requires careful planning for consumables and potential equipment failures. Despite these challenges, the allure of Mars remains strong. NASA's Artemis program, which aims to return humans to the Moon, is explicitly designed as a stepping stone for eventual Mars missions. Private companies like SpaceX are also developing technologies with Mars exploration in mind. As we continue to push the boundaries of space exploration, Mars stands as the ultimate destination, a world of scientific wonder and potential future home for humanity. The journey there is fraught with challenges, but each obstacle overcome brings us one step closer to setting foot on the Red Planet. From the precise calculations of launch windows to the heart-pounding moments of atmospheric entry, getting to Mars represents the pinnacle of human ingenuity and determination. It's a testament to our species' innate curiosity and drive to explore the unknown. As we look to the future, the red dot in our night sky beckons, promising new discoveries and the next great adventure for humankind.